Sorry, we can welcome the following speakers. So it's Thomas Fruleux. He's a postdoctoral researcher here in Cura. He's working on the fabrication of cellulose-based membrane for artificial lung application. From 2020 to 2023, he did his PhD in the University of Bretagne Sud in France. And he's also involved in raising awareness about plastic use, life cycle, and issues related to environmental and human health. Thank you, Thomas.
Thank you, Lily, for the nice introduction. Hi, everyone. So today I would like to present you a project that we're working on with our team, composed of Jimin Wang, Catalina Valero-Giraldo, under the supervision of Manu Speaks. So the title of this project, the aim of this project is to develop cellulose-based membrane for artificial lung application. And this is part of the cell membrane project that I will tell you about. So the purpose of this project relies on lung disease. So lung diseases is the third most frequent cause of death worldwide. And the only long-term solution to that is to do lung transplantation. But as you can see on this graph, over the years, so from 1990 to 2020, there have been an increase in the gap between the number of people that are receiving a lung transplant and the number of people that are waiting for it. So because of this gap, I don't know if you can see, no. Do you have any lighter? Anyway, I'm good like this. So because of this increase, scientists worked with extracorporeal membrane oxygenator, which is called ECMO device, which represent a bridge to transplantation. So it looks like this. It's not moving anymore.
The connection.
Yeah.
Fine.
I have at least one little problem with slideshow, so that's fine. Maybe I'm out of it, yeah.
Move it all the way to the opposite side. Yeah. Matt, would you walk up here so the camera can?
Okay, right here. Yeah.
It's looking at
the camera right here.
Okay.
That's not going
back. Yes. Come on, camera, come here, please. Still on. What is with the camera focusing on? Maybe someone can come with me. Manus, I think it's you.
Maybe it's that new aftershave, I know.
Yeah, maybe because you were there.
No, it's okay. I think
That's fine.
You can come here. I think here.
Right here.
No, I changed. I put
Okay.
another sheet. I think it should not move.
All right, so let's start again. It does not fall. Still on the side. But yeah.
It's not. It's focusing on someone.
It's focusing.
Oh.
Or otherwise, I can just go there and. Yeah, now it's better. Thank you, Lali. All right. I think it's okay. Yeah, that's all the room. So coming back to this artificial lung application, so the ECMO boxes that I'm telling you about looks like that. So inside the ECMO, you will see fibers like this, so you can have a look. And so the idea of this box is it allows people to have breathing functionality before a lung is transplanted. So to give you some figures, the cost of the ECMO treatment goes between $40,000 and $150,000. There is a costly day support of $5,000 to $10,000. The lifespan, that is an important parameter, does not go usually above 10 days, which means that after 10 days, if the person is still under in a critical state, they have to do clinical operation to change that. So which is sometimes problematic. And there is a blood flow capacity which goes between 3 and 7 liters per minute, which is comparable to the blood flow capacity of a human lung. So it's kind of comparable. But of course, this little ECMO device today present some limitation. The first one is what you will find inside it. So that's why I shared with you some fibers. So you can see the fibers that are in the plastic bags. They represent what is inside the device. And so the blood goes around the fibers while the oxygen goes inside the fiber. So there is little holes that allow the oxygen to go through. And so the gas exchange occurs at this area of the device. But today, because the blood flow follows a uniform, it has a uniform geometry, so the blood flow can go a little bit where it wants to go. So it generates sometimes turbulent flow, and it will impact, of course, the lifespan of the device because it will generate blood clotting. So that's the main problematic today with ECMO device. And that's why also they have to change it after 10 days, because usually there is blood clotting that prevent the blood oxygenation because of the blood transport, which is not optimized. So it's like structural aspect here to modify. Then if you look at the material, so that's the little fiber. So if you look at these holes that where the oxygen goes, it is made of what we call polymethylpentane or polypropylene, which are two petrochemical products that are used here because they can be easily designed, but they are not hemocompatible. And so that's also a problem, because if the material is not hemocompatible, you have to treat it with heparin coating, and you have to use anticoagulants for the patient to allow him to breathe. So that's another limitation of this material. If we can work with something more hemocompatible, we will not have this blood clotting problem. The third one, I focused on the last parameter of this table. It's the surface area. If you look at all of these fibers, the surface area represents 3 square meters. Compared to the human lung, there is 70 square meters of surface areas, which means that even if we have the same blood flow capacity, we don't have the same efficiency of oxygenation of the blood, which means that when people use that in hospital, they keep breathing, but in a very critical state, usually it is estimated that when you breathe with this ECMO device, you breathe at 30% of your own efficiency, your own lung efficiency. So which is still a big difference. And finally, on top, there is a last parameter that I'm very sensitive to, which is of course, this material is not biodegradable. So at the end, it will result also in increasing the plastic waste, which is generated in hospital. So all of that said, and I'm going to spend a huge time on the introduction for this presentation, but that's part of the cell membrane project. We want to develop a cellulose-based membrane for artificial lung application. So this project gathers 6 different teams in Europe. The leading team is Smart Reactor, so located in Galway. Then there is our team at the University of Galway, and there is a company in Sweden, which is expert in bioprinting, so CellLink. And then there is different University of Tübingen, expert in hemocompatibility device. And then there is Brunel University in London and the University of Lisboa, Nova, which are expert in formulating nanocellulose. Now there is something I did not explain to you, is why do we want to use nanocellulose? So nanocellulose, for those who are not familiar with that, is the most abundant natural polymer on Earth, with a production of 25 million tons per year. So that's what we use. And so if you want to work with cellulose, you need to look at, of course, natures. And inside the trees, there is fibers. So if you take, for example, in this part of the tree, you will see a lot of fibers like that, which are mixed with polysaccharide macromolecules. And if you look at these fibers, you can go deeper and deeper inside the fibers. So there is the microfibrils fibers, then the nanofibrils, and you will get these final tiny molecules, which are called cellulose molecules. These 2 different regions, there is some very organized region, which are called the crystalline region, and some less organized region, the amorphous region, can be separated by different treatment to get cellulose nanofibers and cellulose nanocrystals. And that's what we are using today to produce this new artificial lung. The potential of using this kind of product is that it has a high surface area. Because you work at the nanoscale, you will increase the surface area. So we think we can increase the efficiency of the gas exchange properties inside the device. It's also cytocompatible and hemocompatible. So compared to the common material, that's a huge improvement. It would be a huge improvement. It's a green material. It has high mechanical properties, so it can overcome blood pressure. It can, resist to this kind of mechanical stress. And then it's also biodegradable, so it can help to reduce or at least limit the waste which is produced in hospital. And finally, it has So a broad possibility of surface modification, which means that if you work with cellulose, but you see that the cells are not going that well on it, you can modify the surface chemistry of the material to make it more hydrophilic. So it's something which is good because with this material, it's kind of like feasible to change the surface chemistry. So that's what I mean by this last point. So the two materials we worked with is a nanocellulosic film. So I'm going to show you more samples. Maybe I did too much. So that's the second one you can see. And maybe feel free to have a look at that. So it looks like this for now. So that's the first material we have been working with, a flat nanocellulosic film and an electrospoon membrane. So this one is more porous, more hydrophobic. It has a high aspect ratio. So if you want to know more about this manufacturing process, it was done by our collaborators in Brunel University. So the idea behind that is that you use a polymer solution with the nanocellulose powder here, and you will generate like a high electrical field between this part and the collector. And so the fibers you can see are here, and they are like directed toward the collector in a very thin shape. So it helps you to create something which is like super tiny with very small dimension to help increasing this surface exchange area. So once we selected the material at the beginning of this project, we needed to look at the cell-material interaction to be sure that our cells, which are the endothelial cells, are happy with this material, so they can contribute to this artificial lung. So once we are okay with the first cytotoxicity standard, we need to look at how are the cells communicating together. How strong is the barrier that they might create on top of our device to get this final little idea of. So here is the membrane, and the cells in our perspective will be inside like this, and they will cover the entire surface of the material. And then inside you will have the blood vessels that will circulate. So that's different than compared to what I just showed you, because they put the oxygen inside the material. But here we want to put the blood vessel inside to increase once more this surface exchange area. So at the end, it will be the opposite. The carbon dioxide will go out and the oxygen will go in. Hope you like that. Important. So just to give you very quickly some results, we looked at metabolic activity of the cells and the increase of the cell number over time. So if you see like from day 1 to day 21 on the left, you can observe that there is an increase on the 3 materials. So the control is a tissue culture plate until reaching something at 3 weeks, which is not comparable, but there are still an increase of the metabolic activity, which is combined by an increase of the cell number. So we can conclude that the cells are able to proliferate on these 3 materials. And even if it's slower to happen on the nanocellulosic membrane, which is the most, I would say, the material that we really believed in, they can still settle at 3 weeks of interaction. So more picture about that. So here you can see the nucleus of the cells on the left and the cytoplasm on the right. And the most important, I would say, pictures are this one. So here you can see for the nanocellulosic membrane that at day 1 and day 7, there is a slight increase, but we are still building a very like small cellular network. While after 3 weeks, you have this, what we can consider to be an endothelium, which could help us to cover the entire surface of the material. So the results in terms of cytocompatibility are good so far. Then we wanted to know, okay, if you look at this endothelium, how good is the connection between cells? So we looked at another connection between them, so a cell-cell junction, which is called V-cadherin. And you can see, for example, at day 3, on the top left here, for the control, after 3 days, you already have this, the in-between connection between cells, which proves that there is a nice adhesion and it will give a nice permeability function to the layer. So these molecules are important because they allow to provide nutrients through the blood tissue, through the human tissue to the blood vessels, and they can also prevent the foreign body to go inside the human tissue. So they have a big role to protect our body from potential like harmful product. And then after 14 days, you can see that the control still have like a very even bigger endothelium. While for the nanocellulosic film, you have also the creation of these adhesions of these molecules connection, which is nice, which proves that the cells are happy with this material. But for the last material, which is processed, we do not get a nice endothelium formation. And we think that right now there is different things we could optimize, especially the structure of the material, because this one is very porous and very soft, so they don't really manage to nicely settle on the material. So it's still something that we are optimizing. I'm not going to go through that, but we did different tests to check how good was this endothelium by using electrical test, which is called TER measurement. So I can tell you more if you want about that after the meeting. But I prefer speaking directly about what we are doing right now. So we received a lot of formulation for our different colleagues. So that's the film that I gave you. So please don't hurt them. But it's now the thing we know is that, okay, before we had a very porous and nice nanofibers, but it was too weak mechanically speaking. So what we want to look at is, okay, with film like that, which are processed with different formulation. For example, here you have bamboo fibers with nanocellulose. You can have more flat structure that could help the cell to be like maybe more connected together and be able then to imagine an interaction between our material and the blood on the middle term. So that's the thing, testing more formulation and also thinking about the final architecture. So on that part, we used Celllink's expertise in this domain with bioprinting to check which kind of architecture we want to test, because we need to also think about, oh, okay, how big needs to be the channel if we want the cells to be okay, but also the blood to be circulating in a laminar flow. So we want to avoid the turbulent flow in this device. And finally, something that I also need to mention is we tested everything in terms of cytocompatibility in static condition, but in our body, the blood is always circulating. So the cells are always soliciting, like always stimulating. So we need to do this test under dynamic conditions. So that's what we are also planning to do with a culture chamber to see how would the cells be connected to these different materials by changing the shear stress that we applied on them. So that's a lot of perspective, but that's right now where we are. And we are going to work also with a more maybe suitable cell line for this project, which is the ULEC 5A, which are the microvascular cells that are present in our lung. So that's all for this project. I just want to take this few minutes to speak about what you just said, Olali, before. The same project that I'm having with the EP department, so the public engagement department, aims to raise awareness about plastic collage. So this workshop aims to play a game to understand what is exactly the problem with plastics in terms of formulation, creation, end of life, the challenge of recycling, but also at the end, what is the real impact on health and on environment. So it's a card game. If you want to have a look, I have it here. And so there is 4 different sets and you play as a team. So it is based on collective intelligence. It lasts 3 hours. So that's a commitment, but you can also find other version for 1 hour. Few people here did it, and I think they had good time. So just don't hesitate to speak with them. But also, if you want to speak about science communication or other tool you would like to create like that, I will be happy to discuss with you about it. So just to give you final figures, 9,000 people played this workshop all around the world, and there is 5 workshops that were given in or from Ireland this year. So you can see the pictures. So in-person workshop, but also online workshop. Feel free to really discuss about that. I'll be very happy to help you. Thank you, everybody. And please, if you have any question, don't hesitate.
Questions?
I was curious about the cell line that you used to do the endothelium inside your device. Would it affect the compatibility depending on different patients if you use only the same cell line, or would you be great to adapt or even develop an endothelium from the patient side cell directly?
The idea would be that with the final device to use like the people's endothelium cells to create this because it needs to be, you're right, suitable for the patients. So that's the final idea of this project. But for this test, we use primary endothelial cells with 3 different donors to have an idea of how good was the endothelium formation for these 3 different donors. But you're right, that's something we need to.
Really cool work. My question is, you looked at adherence for cell-cell interactions. Have you thought about looking for integrins for your cell ECM interactions, like if the cells are interacting with the nanocellulose membranes?
That's a good question, actually. No, I haven't looked at that because to know how you proceed to do this test, because
I can talk to you about that afterwards. So yeah,
like in terms of protein expression,
it's just IHC. It's actually it's the same way you do your cadherin stains. You can just get integrin stains as well. So
okay,
yeah.
Actually, yeah, that's my colleague Jin Wang is very like expert in flow cytometry, and I think he's thought about that.
Excellent.
So, yeah. Something we look also. Yeah.
Thank you. Nice talk. If I understand well, for the patient, so the blood of the patient will touch this endothelium, right? This membrane. So isn't it necessary to check maybe later the bodily immune reaction to this kind of cell membrane?
It will be,
Could
yeah.
be problematic.
Yeah, exactly. Actually, we also checked that, for example, the inflammatory response that could, be generated from this interaction. So that's not something I presented here, but we have the results. I just wanted to focus more on the introduction and to explain really the project. But yeah, we checked about that if there is no inflammation from day 1 to day 21. But yeah, you're right. Like, usually the difference between the membrane we are trying to develop and the membrane which is already commercialized is that there is endothelial cells in our membrane, so it's more like bio-inspired from our body. While the membrane which is used today is just like full of coating, which allows the blood not to attach to it, but usually it happens after a few days. So that's the idea. So we need, of course, to be sure that there is no bad body reaction after that.
Do you know what the difference between the crystalline and the amorphous cellulose? Is it like clinical difference or is it like the way you process?
So we don't process it actually. Like, so I'm not an expert on that part, but I think the main difference is structural. I think the chemistry is the same. It's just how your fibers will be arranged.
Okay.
And so, of course, it will give you, like, if you process something which is full of nanocellulose fibers or nanocellulose crystals, you will not have the same, class transition temperature. But I don't think about like how look the fibers at first. I don't think the chemistry, the groups you will find in it are different.
Then you can go from one to another.
Yeah.
Any other questions?
Actually, there is work on that, like when they try to process it to make the crystalline region higher, by changing the cellulose treatment. Yeah.
Thank you, Thomas.
Yeah, welcome. Thank you.